Okay, hello. Good afternoon to everybody. The first of all, thanks to attending this webinar, the first of many according to our commitment to sharing knowledge. Let me introduce myself and my company. My name is Juan Moreno Cid. I am an R&D engineer and pilot plant manager at BIONET. I'm holding a PhD in biotechnology with a background in fermentation technology at different levels, science lab and pilot plant scale as a head of bioprocess development, up to large scale as the technical manager in agri-food areas. At BIONET, we are manufacturing of lab, pilot and industrial equipment and software focused to bioreactors, fermenters, tangential flow filtration, as well as bioproduction plants, in which we integrate our proprietary equipment with technologies from other leading vendors. Briefly, the content of the webinar will be divided into an introduction, the explanation of a methodology based on 5 big steps to consider a scale-up, conclusions, and finally a time for questions in the platform. So let's start like everything from the beginning. But what is scale-up? Process scale-up, in a broad sense, is a critical activity that enables a fermentation process achieved in research and development to operate at a commercial viable scale for manufacturing. A successful scale-up involves many aspects of successful preparation and planning beyond pure process scale-up technology. Simple concept in theory, but sometimes complex in the practice. Scale-up means the art for designing large-scale apparatus or full-size plant using the data obtained from the lab studies. The main objective of the R&D stage is to turn an idea into a product obtained through a process on a reproducible and cost-effective commercial scale. Lab scale is focused to demonstrate process feasibility or generate design data for a process. Then a mini plant may be more appropriate than a pilot plant. Includes all recycled steams and can be extrapolated easily. Use the same components as the lab testing like pumps, which is often standardized and can be used in many other mini plants. Operated continuously for weeks or months, so some automation is required. Is used in combination with process modeling and simulation of the industrial scale process. This stage is to provide master manufacturing formula, identify the critical features of the process, evaluation, validation, and finalization of the process. Also obtain the guidelines for production and process control, review of the processing equipment to produce physically and chemically stable products, and conduct lab studies and scale-up planning at the same time. Pilot scale means an experimental system that represents the part it corresponds to in an industrial unit. A pilot plant allows investigation of a product and process on an intermediate scale before large amounts of money are committed to full-scale production. It's not possible to design a large, complex product processing plant from lab data alone with any degree of success. Producing small quantities of product for sensory, chemical, microbiological evaluations, limited market testing, or furnishing samples to potential customers. Shelf-life and storage stability standards. Determining possible byproducts or waste stream requiring treatment before discharge. Providing data that can be used in making a decision on whether or not to proceed to a full-scale production process, and in the case of a positive decision, designing and constructing a full-size plant or modifying an existing plant. After this brief introduction, we are going to start with a methodology to apply a scale-up taking account 5 big steps. Part of the structure of these steps are basically concepts of process development. But finally, the main target of applied research and process development is to reach the commercial scale for the production of the target product successfully, minimizing risk. Thus, we can divide a proper methodology as step 1, microorganism R&D, step 2, process R&D, step 3, criteria for scale-up, step 4, scale-up calculations, and step 5, scale-up validation. Step 1. Before jumping into process development, have in mind the next consideration for the scale-up: knowledge of the microorganism and target product. Select key performance indicators, KPIs. These will be the basic and preliminary considerations for the scale-up. Regarding the knowledge of the microorganism and target product, it's important to know the behavior of the microorganism in the media selected and the technique for production, the type of bioreactor will be used, submerged fermentation in a stir-tank bioreactor, or air-lift bioreactor, solid-state fermentation, etc. Main characteristics of the target product, the main specifications to ensure that we are producing in the quality and functionality required, and the definition of the analytics will be necessary to determine the target product, biomass or biomolecule. Key performance indicators, KPIs, are performance metrics that measure the development and specific goals for the process. For that reason, the definition of our KPIs must analyze and evaluate the performance of our process, and in the scale-up, how far or close we are from our desired process from the development at the small scale. Some examples of microbial fermentation process would be biomass concentration, turbidity or optical density, total cells, target product concentrations, levels, potency, titers, and the specific growth rate. Okay, next step will be process R&D. We can divide this step into 3 topics: media definition, grade or raw materials, process control strategies, main parameters, and operation mode. Consider the right selection of the media for the scale-up, because at a small scale, it usually is easy and relatively cheap to use some media. But we must have in mind the scale-up. The main objectives for the formulation of the media and considerations when are selected at the R&D stage are to obtain the maximum biomass or biomolecule yield per gram of substrate used, maximum concentration biomass product, the maximum rate of product formation, minimum risk of undesirable products called bioproducts, and these red ones are considered for the scale-up. It's very important to take account good supply availability of medium components in optimal quantities and good quality during the production period. Minimum problems in medium preparation and sterilization. Minimum problems affecting process parameters, dissolved oxygen, aeration, agitation, and downstream processing. And minimum problems in the safe disposal of effluents and waste treatment. Okay, so, oops, sorry. Okay, this is. Regarding the effects of process parameters on biological performance are critical. The main objective of bioreactor selection, design, and control is to provide the optimal environment for biological reaction system. The bioreactor should provide optimal conditions, like temperature, pH control, oxygen transfer, mixing, and substrate concentration. In addition to its basic function of containment, Therefore, the process control strategies must be well defined and then select in advance the sensor that will be necessary. Definition of the operation mode to be applied. Okay, there are three main modes of fermentation mode: batch, fed batch, and continuous. Most industrial fermentation processes still operate as a simple batch or fed batch. At the moment, there are few continuous fermentation processes in the industry. The continuous process increases the process of productivity and is a cost-effective process, and some additional advantages like the control of a non-desired substance or toxic compounds producing during the growth. Nevertheless, it's not always possible to establish this mode by regulatory limitation. Not all products can produce in the log or exponential phase, which is the main goal of a continuous process, to maintain the culture in this phase, or contamination risk, mutations, or technical limitations. So for that reason, it's convenient to choose the most appropriate and feasible optimal operation mode that we can apply depending on the limitation of our microorganism or target product. So in consequence, do we have all the tools we need to apply my operation mode and covers the technical specification according to the needs of my process? In this sense, it's very important to foresee the ancillary equipment and the technical specification will be needed. For example, a variable speed pump for fed batch, we must cover the flow rate in the range of my microorganism will need, or special modules with synchronized variable speed pumps for continuous process or a scale if we want to control the level accurately, additional sensors, etc. But always consider to thinking big. I mean, the conditions of the operation mode, flow rates, lines, vessel capacities for additions and collections, how to sterilize the media to be added, how to collect the final or intermediate product aseptically if is necessary. All these considerations must be taken into account when evaluating whether the process will be scalable in a feasible way. This topic is very wide. If you want more information, you can visit our special content area in our website of knowledge. Here you have the link. This is very interesting site. Okay, so now we have the knowledge and the main information, at least at a small scale. Step 3, criteria for scale-up. We must consider to know technical specification of the main equipment, bioreactor fermenter as the heart of the bioprocess, and the definition of the strategy or criteria for the scale-up. It's very important to spend some time with love to get to know our bioreactor and its characteristics. Geometry, types and dimensions of impellers, range of gas flow, maximum power of the stirrer, maximum working volume, range of flow rate of the switch pump, range of the speed of the stirrer. This small exercise can save a lot of time when uncertainties appear and for designing the installation, deviation in the expected yields of productivity, and if it's necessary to do a cause-effect analysis of these deviations. The definition, strategy, or criteria for the scale-up. So, do you know the equations you will need? And now we know more about our tools, thus we must select the criteria for the scale-up. The most commonly used criteria for scale-up from lab scale to pilot scale and from pilot scale to production or plant scale fermentation is to keep one or more parameters similar between various scales. Usually, it's impossible to maintain all the parameters in the same ratio to one another. These parameters include constant power input per unit bioreactor volume, the constant impeller tip speed, the constant oxygen mass transfer coefficient, oxygen transfer rate, OTR, Mixing time, the time defined as the time taken to achieve a specific degree of homogeneity following agitation, and a constant Reynolds number. Most industrial microbial processes are aerobic. Constant dissolved oxygen concentration is also used as a scale-up parameter for production. For the scale-up of aerobic fermentation, the effect of gas-liquid mass transport is the most significant factor. Therefore, a scale-up in aerobic fermentation is often performed based on keeping the volumetric mass transfer coefficient, KLA, constant. For example, in bioreactors, adequate mixing is essential to ensure the adequate supply of nutrients and to prevent the accumulation of toxic metabolites. For a bioreactor designed for a suspension system, mixing time is a critical parameter to be studied and evaluated. The fluid hydrodynamics, fluid rheology, impeller type, power input, and vessel size can all influence the mixing conditions. For that reason, remember from step 2 of this webinar, it's very important the selection of the right raw material thinking in big. Step 4. Scale-up calculations. When we have selected the parameter for the scale-up, it's necessary the definition of the method for the determination of the parameters selected to maintain between different scales. For example, the experimental determination of the volumetric mass transfer coefficient, the famous KLA. The determination of KLA in bioreactors is essential to establish aeration efficiency and to quantify the effects of the operating variables on the provision of dissolved oxygen. Several methods have been developed to determine the oxygen transfer rate in bioreactors, chemicals and physicals, but so far, the most common and simple method used is the physical dynamic method, based on the measurement of dissolved oxygen concentration in the liquid during the absorption or desorption of oxygen in the solution. In the dynamic method, the liquid is deoxygenated by stripping the oxygen with nitrogen. Then, the dissolved oxygen concentration in the liquid is measured and the equilibrium is reached. You can see here following in this graphic. So we start supplying with nitrogen in this point to strip all the oxygen present in the media. So in this point, we start again to supply with air till reach the equilibrium. So from the slope of this representation, we can calculate the KLA. On the other hand, for the determination of the oxygen uptake rate of our microorganism, in a similar way that the dynamic method for the determination of the oxygen transfer rate, a technique proposed by the authors Taguchi and Humphrey, measuring the respiratory activity of microorganisms which are actively growing in the bioreactor. In the previous determination of the KLA, for the characterization and calculation of the oxygen transfer rate, has been done without any microorganism growing in the bioreactor, just the liquid, the media. For the next exercise, for the calculation of the oxygen uptake rate, is using the microorganism. So, to calculate the respiratory activity of the microorganism, if the gas supply to the bioreactor is turned off, the dissolved oxygen concentration will decrease at a rate equal to oxygen consumption by the respiration of the microorganism. Under this condition, the oxygen uptake rate can be calculated from the slope of the plot of the dissolved oxygen concentration after stopping airflow versus time. Biomass concentration must be known or measured at this time to know the oxygen consumption rate per biomass unit. These calculations will allow us to design and scale a system that supplies the sufficient oxygen that our culture will require and that our equipment is capable of transferring. Okay, impeller tip speed. Agitator tip speed like criteria has some advantages in the case of bioprocesses with sensible microorganisms over cell stress produced by a stirrer, because it determines the maximum cell stress in the tank, determining the possible cell damage, and also influences the stable size of flux and gas bubbles. However, its use entails a reduction in the power input per unit volume and in the stirrer speed, which causes a remarkable reduction of the rate of oxygen transport. Remember from step 1 the importance of the knowledge of behavior and use of our microorganism in the media and type of bioreactor used for production. You can see in this comparison with just a bioreactor relations 1 to 10, the variation of the agitation keeping the same impeller tip speed can be very high. For example, it's a common mistake if we apply 500 RPM at 3 liters and I want to apply the same agitation at 30 liters. We are applying 60 more impeller tip speed at 30 liters than 2 liters. Instead, to give 1.4 meters per second, we are giving 2.26 meters per second. Okay. Power consumption. Okay, power input. Power consumption is a significant part of the operating cost of our large-scale systems. To calculate the speed, one way to obtain the net power input per unit volume can be measuring via the electric power of the stirrer in watts. So if we can obtain this information from our equipment, we can calculate the power input in watts per unit of volume of the bioreactor. The different scale-up criteria normally result in an entirely different process conditions on a production scale. Usually, it's impossible to maintain all the parameters in the same ratio to one another. The consequence of such calculations for two geometrically similar steel tank reactors with the model system volume of 3 liters and the production system volume of 30 liters with a linear scale-up factor of 10 is shown in the present table. In practice, all 4 methods are used in combination with each other, and sometimes the trial and error method must also be included. In general, it's impossible to scale up a bioprocess keeping all conditions in the optimal values, and it's necessary to choose which variable is considered as the most important. For the scale-up of aerobic fermentation, the effect of gas-liquid mass transport is the most important factor. Therefore, scale-up in aerobic fermentation is often performed based on keeping the volumetric mass transfer coefficient KLA constant, or if the concentration of oxygen is negligible compared with the concentration of oxygen in the equilibrium in the culture broth, keeping the oxygen transfer rate also constant. Then, in practice, usually the best criteria for scale-up are to maintain the power input per unit volume or the volumetric mass transfer coefficient constant. Step 5. Scale-up validation. The success of the scale-up process must be confirmed by experimental results which show that there is no difference between small-scale and large-scale fermentation carried out under the same criteria selected for the scale-up, like the oxygen transfer rate. It's the moment to track the KPIs defined at the early stage of the process development from step 1. On the other hand, although the kinetic parameters of growth and oxygen consumption of microorganisms must be scale independent, The growth rate in a bioreactor is scale dependent because of the scale dependency of oxygen transport rate. Another aspect making the situation more complex is that some operation conditions necessary for adequate mass transfer can produce negative effects. The local environment of the cells in large-scale industrial bioreactors varies over a higher range than in small lab bioreactors, because of the high heterogeneity of the cultivation medium caused by the longer global mixing time, the turbulence intensity, and thus local shear forces are exacerbated with the increasing scale of bioreactors. Under this condition, cellular stress can affect the growth. The time required for the transition from lab scale to manufacturing is typical 1-3 years. Depending on the grade of the novelty of the process, the scale can be done in one stage for a simple process or 2 stages for more complex and novelty process, requiring the first stage with a pilot plant and a second stage with a demonstration plant before the commercial scale. Remember, minimize the risk of large capital investment in the full-scale manufacturing plant by further validating the process. Therefore, we have to be patient, methodical, and constant, and love what we do. And to finish, some conclusions. Many parameters impact the performance of the fermentation process, and most of these are subject to change during scale. Lab-scale process development must be conducted under conditions that mimic as close as possible the intended large-scale manufacturing process. The process parameters can change either due to cost constraints or equipment design and scale. Have clear the strategy to be applied from the beginning according to the knowledge of your process and the tools available. Choose scalable and reliable parameters. Be methodical, patient, and love what we do. As I said at the beginning, there is going to be some time for questions. We'll be online for a while answering them and publishing the ones that we think are relevant. Please, when making a question, leave your email so that we can answer them and provide you with supporting information material. Okay, I'm delighted to present and invite you to the next webinar of Downstream, titled Tangential Flow Filtration, a key step in vaccines production, with my colleague, Dr. Ruth Ordóñez, our downstream specialist. Okay, and again, thanks for attending this webinar. I'm really happy sharing this moment with you. I hope you find this webinar useful, and we wait you in our social networks, Facebook, LinkedIn, or our website, www.bionet.com. Here is an email if you want more information, and we'll be happy helping you in your idea or project related to the bioprocess world. And on behalf of all my BIONET colleagues and BIONET, thanks.